can estimate period is 2 pi a squared over mu. So we calculate the a already, so we plug in here the t should be equal to 21942 seconds. So about 1/4 of the day, and that is about 6 hours, okay. So given this kind of the orbit, so basically it will around the Earth 4 times a week. The sixth one, the true anomaly. When at r equal to 1, 3, 5. So this one is about the orbit. So we simply taking this 1 plus e cosine nu. So here the t equal to h squared divided by mu, and 1 plus okay, so r equal to 13560. So we simply solve for the two equations. Then we know the h, we know the nu. So therefore here we can solve for nu. Cosine nu equal to minus 0.3337. Okay, so if we punch the calculators, we see this trigonometry here. If you punch in the calculator depends on, I think the calculator will give you only one number. And that number should be 109.5. I don't know. I don't know how to play the TI. I don't have a TI calculator. My calculator is the one I bought it when in the first year go to the graduate school. So that's a long time ago, 100 years ago. Okay, but that one gives me the two numbers. So how many numbers you got? Only one. Which one? Is this one? Okay. Actually, this is another one. So here is about the trigonometry. Let me make a point here. So say cosine. So that's a cosine. And right now we are calculating is minus 3337. So basically here we are given this is minus 0.3337. So here you see we make the intersections. We're looking for is these numbers, and that is a 1, and that corresponding is the 1.109.5 degrees. Okay, but also this will be another solution. This will be another solutions. But between the range 0 and 2 pi range, because for our orbit, you can see this is a set, and this is the true anomaly. The true anomaly, once they go to the cycle, they will swap about 2 pi. So here we should looking into any possible answers in this range. And here this is 2 pi. So basically you expect we should have 2 answers. And calculator only will give us this one. You need to figure out this one. And how to do it. So basically you can see this one to here is how much? So the 2 points are symmetric with respect to this one, right? So you should be able to figure out this number. This number is 180. So that should be about 70.5 degrees. So you simply added up 180 by 70 0.5 degrees, so that is 250.5 degrees. So this number corresponding is 250.5 degrees. You need to do this one by hand because the calculators, they won't give you the two numbers. But here, for this case, let me show the two positions here. So 105, so one answer is here. So you calculate it is 109.5 degrees. So that's a position one. The other position actually corresponding is here. Symmetric respect to the the major axis is symmetric to there, and this is the second position. So that second position is the angle we measured from here to here. That is 250.5 degrees. Got it? So these are two possible locations on the orbit, and here I look for is two solutions, complete solutions. Because in this location, in that location, the distance will be that. Okay. Otherwise, if you would have a more specific, then we would have only have one solution. But here we only confine our true anomaly at this distance. Actually, there's two possible distance values on the orbit. Okay. Good. And then the sixth one and the speed of the set at the same locations. Okay, so the speed how can we calculate speed? And if we know the distance, if we know the true anomaly, and we can correlate speed, speed can be correlated to the radius by, they both appeared in one term, is if you remember in mechanical energy. So that will be our starting point. So mechanical energy is minus mu divided by 2a, and also equal to v squared minus mu over r. Okay, so we can use this one. So using these equations, therefore we can calculate V equal to plugging everything 5.94 kilometer per second. And combining for 0.6, if you keep changing the radius of R value, actually you should be able to dig out the point wide, the speed of the satellites at any point, at any location on the orbit. Okay, so for example, at this point, we calculate it's 5.94. So here is the largest one, and that is how much I forgot, 9 point something. Then gradually reducing its speed to here and until reaching 2.9 something, and then from here it's gradually picking up its speed, approaching until reaching the maximum. And as far as here, what is the speed here, then you can repeat the step here. You can actually calculate the speed at any point. Okay. The STK also have such a functionality, can give you this kind of information. And the 7. The flight path angle, phi, at r equal to 13560 at the same locations. So at the same locations, we simply want to calculate flight path angle. Flight path angle is this is the radial distance. So this is the normal to the radial distance in the local horizon, and this is the speed. So this is our angle phi. And before doing that one, we expect the angle should be positive. Okay. So from here, so let me do this one. So this is the orbit. Focus. So this is the phi. Okay. So H equal to R V cosine phi. We use this value. So 65750. So again, from here you should be able to find cosine phi equal to certain numbers. I don't have this number yet. And then simply phi will be a cosine of this number. Back to our similar process, a cosine, we expect they should have two numbers. But here again, in my analysis from this drawing, we expect positive value. Okay, so whatever you're going to do the trigonometry, for two possible values here, we only pick one. So that is 35.3 degrees. You don't need to give me 2. If you give me 2, then you get half points. Got it? And that is the basically we fit into all the graphical physical observations of the problems. So that is for the problems today, and we will have more exercise coming up when we go to the parabolic, hyperbolic sections, and we have one more kind of complete set of the exercise like this. Yes?
Where did we get the R equals 13,560 from?
Which one? R value?
Yes.
Oh, that's a given.
Okay.
So that's a given. So basically from here you can see starting from 6 and 7, we calculate, we determine the information based upon the whatever we define. So maybe in other example I can say, give me this number, say when R equal to something.
Okay, so that was picked specifically for the problem.
Yeah, and then this number has been predetermined because this number must be fit into the given the orbit size, and this number is not absolutely picked. So that is determined by something.
It's not arbitrary?
No, because we have orbit. The orbit has to be defined so well. The size is that big. Yeah, so this number shouldn't be arbitrarily picked. You must be do it exactly. Otherwise, you are doing it a different orbit. But for some reason, I simply pick up whatever the author gives to me. But this number shouldn't be arbitrary. Got it? Okay. Okay. Thank you.